So now we will be discussing the network layer, which is the fourth layer of the OSI model. In the OSI layer, so it's a layer 3, layer 4. So let me know. So it is the layer 3, okay, the network layer, the third layer. So after the data link. Okay, this is constructive. Let's see if so the network layer, okay. So ASI layer 3 provides services to allow end devices to exchange data across the network. So talking about this end-to-end transport, the network layer uses 4 basic processes. Let's see what is this. Okay, so addressing encapsulation, segment, then from packet, encapsulation again, then converting it to bits, then routing it. Okay, we have an exchange of data across the remote network here. Okay, so the four basic processes is the addressing end devices. So the end device must be configured with unique address for identification of the network. So also the encapsulation. Okay. So encapsulation of our segment data into packet. Okay. So it just adds the IP header information such as the IP address of the source and destination host. Okay. So also the routing to other network. So direct packets to a destination host on another network. Then the encapsulation, so reverse process of our encapsulation. So I have network layer protocols. Okay. So we have the IPv4 and IPv6. So encapsulation is encapsulating IP. Let's see. Okay, the transport layer adds a header so segments can be reassembled at the destination. Okay, so it uses segment header here, but for the transport layer is segment, but for the IP packets or layer 3 packets, so from the segment, so it encapsulates it, so it adds the IP header, so which contains the source and destination addresses. Okay. So layer 3 addresses. Okay. So characteristics of IP. So it is designed as protocol with low overhead. So it provides only the functions that are necessary to deliver a packet from source to destination over an interconnected system of networks. Or it is not designed to track and manage the flow of packets. The functions here is performed by the other protocols at other layers. Okay, primarily TCP at layer 4. So characteristics of IP protocol, it is the connectionless. Okay, there's no connection with the destination, so it's established before sending data packets. So there's no, so for example, we're sending an email or a mail, so the destination host does not know that data or email has been sent to him or her. So best effort is IP is inherently unreliable. Packet is not guaranteed. Okay. So the packet delivery is not guaranteed to accept, to received. Media independent. Okay, so the version is independent of the medium referring the data. So this is the work of the layer 2. So that is for the layer 2, the media, the medium that would be using. Okay, so connectionless mean that no dedicated end-to-end connection is created before data is sent. The sender doesn't know that the receiver is present if the letter arrives, or if the receiver can read the letter, or the receiver doesn't know when it is coming. So it's a connectionless communication. So IP best effort delivery. So it does not guarantee that all sent packets will be received. That is the IP best effort. With independent, so can travel over different media. So IP packets can travel over different media. It is the responsibility of the OSI data link layer to take an IP packet and prepare it for transmission over communication mediums. So it is the work of the layer 2, layer 2 of OSI model. Activity, what is IP characteristics? Okay, let's see. Where? So fiber optics cabling can all be used to route the same packet. Media independent. Will send the packet even if the destination is not able. Is not able to receive it. Connectionless. It is not guaranteed that the packet will be delivered fully without this effort. Adjust the size depending on what type of network access. No contact is made with the station. Okay, connectionless. Okay, have managed items. IPv4 packet header. Let's see. Okay, we have the IPv4 packet header. Okay, so have here. Okay, this is a 1 byte and then 20 bytes. Okay, the IPv4 path header, so it contains the version. Okay, that it identifies the IP version. So in this, for example, it's a v4 or v6. Okay, so it identifies this an IP version 4. So it's identifies v4. So next is diff ds. Okay, differential services or diff serve. So what is this? So it's an 8-bit field used to determine the priority of each packet. It's 6 most. Okay, the 6 most significant bits of diff serve is the differential DSCP, and the last 2 bits are the explicit condition notification. So just for priority of packet. Or I think this is the numbering. No. So numbering is for the layer 4. Layer 4 packet. So time to live. Okay. So it's used to limit the lifetime of packet. So it's an 8-bit. So the protocol, where is it? Okay. I used to identify the next level protocol. Common values include ICMP, TCP. Oh, okay. So this 8-bit binary value indicates the data payload, the type that the packet is carrying, which enables the network layer to pass the data to the appropriate upper layer protocol. The common values is the ICMP, TCP, and UDP. And then the source IPv4 and destination IPv4 address. So it's a 30-bit binary value. Also have internet header length. Okay. So just a sample IPv4 header version. IPv4 fields, header fields. Commonly referred to as hop count. So have the time to live. Priority of each packet is different services. Recipient host, so it's a destination. Sending host source or reset to. What is this? Okay, next. Okay. So limitations of IPv4. Okay, so it's IP address depletion. Oh, it's the IPv4 is very limited. No? So limited number of unique public IPv4 addresses and available. Okay. So internet routing table expansion. It consumes these IPv4 routes consume a great deal of memory and processor resources on internet routers and lack of end-to-end connectivity. Okay, because we shared a single public IPv4 address. Okay. So we use the NAT. So this can be problematic for technologies that require end-to-end connectivity. Now we introduce the IPv6. Okay, so there are 4 billion IPv4 addresses. Okay, 4 billion. But for IPv6 we have 340 undecillion. The decagon. The million. So improvements that IPv6 provides, so increase IP address space. So it's 128 bit compared to 32 bits of the IPv4. So improve packet handling, so being simplified, and eliminates the need for our NAT. Encapsulating IPv6. Okay, it's simplified. Let's see, the IPv4, then the IPv6. Okay. We also have the version, name and position, new field in IPv6. We have the flow label. Name and position change in IPv6. We have traffic class, payload length. This is the total length. Next header. Hop limit. Next header is type of service. Protocol. So advantages. So we do not IPv6. We're not using the NAT. Okay. We don't need that for IPv6 because IPv6 is, so there's much more addresses. Again, IPv6 packet header, we have the version. So it just identifies that the packet is an v6. Traffic class is okay. So it's the same with different DS. It's for more priority. So the flow label is suggests that all packets with the same flow label receive the same type of handling by routers. Okay, it's new from the IPv6. The payload length, the length of the data portion or payload of the packet. Next header is the kids data payload type. Okay. The hop limit. Okay, it's the same with the time to live of v4. then the V6 and the source and destination address. So we're doing a Wireshark. So if after we are done with the CCNA1 videos, okay, classify packets for congestion control. Control incorrect. Traffic class, okay. Always set to, what is this? It's a 6, so it's a version. We have the hop limit, the size of the data portion, payload length. Okay. So we are just wrong with the congestion control. So host forwarding decision. So host can send the packet to itself. So by using our loopback address, loopback interface 127.0.0.1, local host on the same network and remote host on the remote network. Default gateway. So we use default gateway for routing our packets to other networks. Okay. So using the default gateway. So what is this? So the host receives the IPv4 address of the default gateway, either from the HCP or configured. Okay, let's see. Default route. The IP address of the R1 interface is the default gateway address for PC1 and PC2. Okay. So we just have the default gateway from our devices on the network. Okay. Network interface. Host routing tables. Okay. So we can use the nets.r and route print on our command prompt to see our IPv4 routing table. So we have the network destination, the mask. This is the default route. So I think this is for the internet, like that. Gateway. So default route. Router packet forwarding decision. Okay. So the router looks at its routing table to determine where to forward packets. So have the directly connected routes. So these are the, in this example, these are the networks that is directly connected to the interfaces of the router, the remote network. So it is obviously it is not directly connected to the interface of the router and default route. So it is the route if we don't have a specific route. So it is the default route we use. So IPv4 routing table. Okay, we use the command show IP route. So we already know this. So we have so this is the EIGRP protocol. It's a dynamic protocol, directly connected. Okay. Directly connected routing table and trees. So we have the C, so directly connected network, and L is the local interface. So more like the default gateway. So it's the L. So that's the route source or code. Source code. The code. So it identifies how the network was learned by the router. Destination network. Destination network, how it's learned in the gigabit Ethernet. So that is the exit interface. Remote network routing tables. Let's see. Road source. This is the destination network. The administrative distance. So it is the trustworthiness. So lower values indicate increased trustworthiness of the route source. So the static route, so we have the administrative distance of 0 or 1, or 1 administrative distance of 1 or 0. 1. So for dynamic protocols, we have the 9P for AIGRP and 110 for OSPF. Okay, metric, so value assigned to reach the remote network. So the lower values indicate preferred routes. Then next hop address, so it is the next hop address. So in this example, we have this .226 next hop address for R1 to reach this network. This is identifies when the router was last heard from. And then this is the exit interface. Next up address. So this is the interface to this is the ingress interface to access other network. So that is the next hop address. Identify elements of router routing table. Elapsed times is, so we have the E. Administrative distance, we have the C. How the network was learned, letter A. Choose the destination network, B. Next up, IP address. We have letter D. Go interface. This is the router as a computer. This is not important. This is routers are designed to address the needs of many different types of branch 1 large piece of it. Let's skip this. Router CPU and operating system. So this router memory. So we have 4 types of memory on our router. So you have the RAM, the read-only memory, the NVRAM, and flash. So let's see. So the RAM is used for iOS image and running configuration file, which is also for the ARP table or ARP cache. The RAM, running iOS, the ARP table. For NVRAM, we have the startup configuration. So in our flash memory, so it includes the iOS files, and ROM. So we have the host. So inside the router, so have the power supply. Let's see, power supply, the shield for one, interface card, so fan, SD RAM. So used for holding the running configuration for and routing tables. The NVRAM. So also have the CPU. And so connect to a router. Let's see. Okay, we have different interfaces. Connect our ports. So we have the gigabit Ethernet, the auxiliary port. So the RJ45 port is used or connected to this interface. We can also use USB. Console ports for initial configurations or to access CLI. Okay. Enhanced high-speed WAN interface. Okay, so this is for the serials. Serial interfaces, DSL, switch ports, and wireless. LAN and WAN interfaces. Okay. Can be grouped into in-band router and management ports. Click the highlighted. So you have the in-band interfaces, management ports. So in-band is are the LAN and WAN interfaces configured by IP addressing to carry user traffic. So Ethernet interfaces are the most common LAN connections, while common WAN connection includes layers and those. So for management ports, okay. So we use the console and auxiliary ports. So used to configure, manage, and troubleshoot the router. So it is not used for forwarding packets. We also have the serial WAN interfaces. Okay. So it is used for connecting routers to external wide area networks. So Ethernet LAN interfaces are used for connecting other devices, which includes switches, routers, and firewalls. Okay, similar to Cisco switch, you have several ways to access the user exec mode or in our command line interface. So we can use the console port, console connection, the SSH or secure shell. So it is a method for remotely establishing a connection with the router and also a telnet. So it is advisable to use the SSH because it promotes encryption in packets. Activity, identify router components, connects router to external routers. So you have the WAN interface. So remotely access the CLI. So you have the telnet or SSH. Internal networking, you have the LAN interface, aux port, a point to manage routers using. I think this is aux port auxiliary. Check. Okay. Packet tracer, so we'll be doing this later. Boot set files. Okay, so Cisco routers and switches load the iOS image and startup configuration file into RAM when they are booted, as shown in the figure. Okay, the running configuration is modified when the network administrator performs device configurations. Changes made to the running config file should be saved to the startup configuration. So we must save our changes to the NVRAM. So in case the router is restarted or loses powers. Okay, we load the iOS Cisco OS from the flash memory. Also load startup config from NVRAM to the running config. Okay, the root router boot up process. Okay. First one is, so it performs the pause and load the bootstrap program. Okay. Next step is locate and load the Cisco IO software. So it is located to the flash memory. So if it's not located in the flash, so the router consults the TFTP server. Also, so the final step is for the configuration. So it loads and locates the startup configuration file. So from the NVRAM first, so if it's not in the NVRAM, so it looks in the TFTP server, and then if it's not on the TFTP server, so it looks on the console. It uses the console now. Show version output. Just displays the information about the version of the Cisco IOS currently running on our router. Activity, the router boot up process. I know. Step 1 is post to the bootstrap. What? Okay. Sa lab activity, I just configuration steps on our switch, on our router. So it's the same as our configuration and switch. Hostname, secure, exec mode, telnet, privilege exec mode, securing passwords, our banner, secure MOTD, configure the management SVI, so switch virtual interface, then saving the configuration. Okay. It's the same with our switch. So I think we need to skip this. Let's see. Enable device name. House name R1. Enable secret class 9 console 0 password Cisco login 9 VTY 0 to 4 password Cisco login exit. So encrypt is service password encryption. So banner MOD authorized processing. That's it. Tracer, configure router interfaces. Okay. We're just configuring the IP addresses on the interface of the router. So we use the, for example, interface gigabit Ethernet 0/0. Just in the description, we added the description to the interface, the IP address, and the V4 address subnet mask. And then do not shut down for us to enable the interface. Let's see. So configure, let's see. The terminal. interface, gigabit, internet, 00. Interface. Show me. Okay. Then let's see. So configure address IP. Address 192.168. Connect one. Description. Non-10. No shutdown. Interface, gigabit. IP address 192.168.8.1. So I need description. Verify interface configuration. So we use the show commands. So show IP interface brief or ping. Show IP route. Interface brief. We're pinging. Okay. Show IP route. Just a couple of show commands. Default gateway for a host. So I think this is assigning a default gateway to our host. Okay. So default gateway is only used when the host want to send a packet to a device on another network. It uses the default gateway. So because we have two LAN here, so this LAN here is on a different network, so we use the default gateway to reach the PC3. Default gateway for switch on. So we also need to configure the switch, the default gateway of switch. So we use for what is happening. I think we're losing internet. Let's see. We don't have internet, we just need to answer this. Saddest. Default gateway for switch. First one, we need delete. Default gateway for switch. So layer 2 switch does not require an IP address to function properly. However, if you wish to connect to the switch, administratively manage it over multiple networks, you will need to configure the SPI with an IPv4 mask and default gateway address. Okay. Okay, use this for remote access. Okay. Let's see. Enter configuration mode. Configure sa IP default gateway. 102.168.10.1. So that's it. Connect the router to alarm. Be doing that later. Tracer. Okay. So we're done. So this is the summary of our network layer. So I think that's it.